Welcome to videos on control systems in electronic circuits. So in this video we shall see signal flow graph, which is a second part of this series of videos. So let us consider uh, a signal flow graph having this type of representation. So RFS is the input and YFS is the output. We have this is the signal flow graph. So we are supposed to find the transfer function of the signal flow graph, which is YFS by RFS, for which we know that we have to identify the number of forward paths, and we need to find out what are the individual loops and what are the non-touching loops, two non-touching loops and three non-touching loops. So let us proceed to find the transfer function of this signal flow graph. Uh, we know that okay, this is the signal flow graph what we are trying to find the transfer function. Now there are four self loops, as you can see here. So this is one self loop which is named as L1. This is G2 into H2, and L2 is this G3 into H3, because we are starting from here and coming back to same node without violating the direction of the signal flow. And we have L3, which is now G6 into H6, and we have L4, which is G7 into H7. And loops L1 and L2 does not touch with L3 and L4. So this L1, L2 are not touching with L3, L4. So we can write delta as 1 minus the individual loop gains, that is L1 plus L2 plus L3 plus L4, plus the two non-touching loops, that is L1, L3 is non-touching, L1, L4 is non-touching. So that's what is here. So this is a gain product of two non-touching loops. And similarly L2 and L3 are not touching, and L2 and L4 are not touching. So this is what is the sum of gain products of two not touching loops, and we don't have any three non touching loops, so that's why delta is given by only this expression. And we have the forward path, which is G1, G2, G3, G4, and one more forward path is G5, G6, G7, G8. So as we can see now, so if you consider G1, G2, G3, G4 as the first forward path, this L3 and L4 are not touching that forward path. So that's why we have delta 1, that is the loop, so which are not touching the first forward path is nothing but L3 and L4. So we have delta 1 is equal to 1 minus L3 plus L4. Similarly, we have the path which is L5, L6, L7, L8. This L1 and L2 are not touching this forward path. So that's why we have delta 2 is equal to 1 minus L1 plus L2. So after knowing the delta value, delta 1, delta 2, because we know the value of P1. So P1 can be written as, now we have considered this as P1, it is G1, G2, G3, G4. So this is G1, G2, G3, G4 multiplied by delta 1. So delta 1 is nothing but 1 minus L3 minus L4. It's actually 1 minus L3 plus L4. So this minus sign is taken inside. So it is 1 minus L3 minus L4. Similarly, this is P2, which is second forward path, G5, G6, G7, G8. That's what is here, multiplied by delta 2. So delta 2 is nothing but 1 minus L1 minus L2. So these two are the loops which are not touching this forward path. And we have this as the delta. So that's what is we have found out in the previous slide. So this way we can comfortably write the transfer function of a given signal flow graph. So let us consider one more signal flow graph, so which is consisting of different loops and the forward paths. And if you can observe from RFS to YFS, the number of ways of reaching YFS from RFS is, as you can see here, it is 1 into G1, G2, G3, G4, G5, G6. So this is one forward path which is named as P1, and we have P2, which is 1 into G1, G2, and you can go up here, this is G7 and G6. So that's what is P2. And we have P3, that is 1 into G1, G2, G3, G4 and G8. So that's what is this P3. Of course, by looking into the signal flow graph over here, we can find the loops as, so one of the loop is, as you can see here, it is minus G4, G3, G4. G2, G3, G4, G5 and H2. As you can see, this is G2, G3, G4, G5 and this is minus H2. This is L1. Similarly, we have L2 which is G5, G6 and minus H1. So this is L2, and L3 is written as G8 into minus G8 into H1. So this is one more loop here. You can see this is G8 and minus H1, and L4 is minus G7 H2 G2. So we have this is G7, this is minus H2 and G2 here. So likewise you can identify there are 8 individual loops are there, and we can find the delta value of this one, and also we can just make out that okay, there are some loops which are not touching each other. So by observing this signal flow graph we can actually find out L5 and L7 are not touching. So I want all of you to just carefully look into what is this L5, L7. So let me just have a look at this L5. This is G4 into minus H4. So this is L5, and L7 is this G1, G2. This is G7, G6, and so this minus H3. So actually this loop is not touching with that particular loop. So that's why L5, L7 is not touching. Similarly, L5, L4 are non touching, and L3, L4 is again non touching. And we can know that L1, delta 1 and delta 3 are 1, meaning the two forward paths P1 and P3 are having all the loops touching to it, whereas second path is not this L5, that is minus G4 into, if you consider this, that is G1, G2, G7 and G6. This particular loop of G4 into minus H4 is not touching this forward path. So that's why this is given by delta 2 is equal to 1 minus L5, which is given by this expression. So we can write the complete transfer function of this signal flow graph as P1 into delta 1 plus P2 into delta 2 plus P3 into delta 3. Since delta 1 and delta 3 are 1 1, so you can write it as P1 plus P2 into delta 2 plus P3, and of course whole divided by the delta, which is 1 minus some of the individual loop gains plus the gain product of two non-touching loops. So this way we can comfortably write the transfer function of a given signal flow graph. Now in this video we shall see how to write the free body diagram of mechanical systems. So let us consider a mechanical system consisting of two masses, and there are two springs connected to the masses as shown here, and we have a friction between M1 M2 as represented by B12, and P1 and B2 are the exclusive frictions for mass M1 and M2. So in order to write the free body diagram, we need to write the acting and opposing forces. As you can see now, this is M2 and this is M1. We are subtracting mass 2 and mass 1, and we know that force is applied in this direction to M2, and there are actually four opposing forces. One is due to the mass itself, and the other is due to the friction of B2 and the friction between M1 and M2, which is B12, and due to this spring constant. So let us assume that because of the applied force, this M2 is having a displacement of x1, this M1 is having a displacement of x2, as we can see here. So B2 is the friction between M2 and the reference. So the opposing force due to B2 is nothing but B2 into the velocity, which is nothing but derivative of the displacement. That's why it is B2 into x1 dot. And because of this mass, we have the opposition to this applied force, which is M2 into the acceleration. The acceleration is nothing but the double derivative of the displacement. That's why it is M2 into x1 double dot. So corresponding to B12, we have a relative displacement for this B12. So this side is moving by x1, whereas this side is moving by x2. The relative displacement of this B12 is actually x1 minus x2. The velocity corresponding to that displacement is x1 dot minus x2 dot. So that's why the opposing force for this mass due to the applied force is B12 into x1 dot minus x2 dot. Similarly, for the spring constant, we have the displacement on either side as x1 and x2 here. The opposing force happens to be the spring constant multiplied by the relative displacement of the spring K12. So these are the opposing forces and this is the acting force. Since M2 and M4 are connected through K12 and B12, so the opposing forces for M2, which is due to K12 and B12, will act like the acting force for this M1. So that's why I can say this is actually pulling M1. So the magnitude is same as the opposing force for this M2 due to K12 and B12. So we have this is acting force for M1 and we have the opposing forces for M1 as due to its mass and the acceleration due to the spring constant and its displacement, which is corresponding to this as x2, and we have the exclusive displacement friction for M1, which is V1 into x2 dot. So once we are through with the free body diagram, so we can easily write the equation by equating the left hand side's force to the right hand side force, which is acting force to the opposing forces. So we end up with writing the integral differential equation where F is the applied force is given by M2 into x1 double dot plus B2 into x1 dot plus the opposing force due to B12, which is having a relative velocity, that is x1 dot minus x2 dot, and due to this spring constant it is K12 x1. So sorry, this is actually x1 minus x2, there is no dot here, and these two forces, which are the opposing forces for M2, acts as the acting force for M1. So that's why I can see it is actually the acting force for M1, which is equal to the sum of the opposing forces. We have the sum of opposing forces for M1 as so. So these two are the equations which are governing the forces acting on the entire system. So this is one equation corresponding to M2, this is the other equation corresponding to M1. So likewise we can write the integral differential equation for a given mechanical system once we can write the free body diagram. So let us take one more example of a mechanical system. Here we have mass M1, there is a friction B1 between M1 and M2, and there is a spring connected between M1 and M2, which is through K1, and we have a mass being represented by M2. This is a B2 friction. So we can write the free body diagram of this as so. So now we have M1 separated here. So there is acting force. So because this applied force, we have a displacement of x1, and we are writing the opposing forces as because of k1 and the relative displacement of m1 and m2, and there is a friction. So because of friction, we have a relative velocity of v1 minus v2, and because of mass, it is the only mass for m1, which is m1 into x1 double dot. Now these two will act like the acting force for M2. So you can see this is now the acting force magnitude is same as this, and it is same as V1 x1 dot minus x2 dot. The opposing forces are due to the mass, which is M2 into x2 double dot, and due to friction it is V2 into the velocity. So we can write the equation for this by just simply writing the acting force on one side and the opposing forces on the other side. So now this is the free body diagram and its integral differential equation. So applied force is equal to the opposition due to the mass, due to the friction, and due to the spring constant. So these two will act like the acting force for M2, and it is being opposed by the friction and the mass. Similarly, we can write for a mechanical system, which is in the previous case we actually considered a translational motion. Now this is a rotational motion. We are applying a torque of T here. So there is a inertia of J3, J1, J2, and J1. So in the next video, we shall see clearly how can we write the free body diagram for such a mechanical system, which takes the rotational force as the torque as its input. can just have a look at, okay, how does a free body diagram looks like. Now you can see this is acting torque, the displacement, and so on. So we'll just have a look at the next video.